Okay, the nerve impulse. Nerves have two states, the resting state. And that's when the nerve is at negative 70 millivolts and the neuron is said to be polarized. The action potential is when the nerve fires, it's excited. And the millivolts change inside the neuron to positive 40 millivolts. It lasts 1 to 2 milliseconds. And we say the state of the neuron is depolarized. Please watch this film. It is critical that you watch these little video tutorials. They will help a lot. Resting membrane potential. A voltmeter is set up and it measures the voltage difference, the millivolts, between the inside and the outside of the cell. And it's in the resting membrane when the neuron is polarized, it is not firing. There's more negative on the inside relative to the outside. So we get negative 70 millivolts. So inside neuron is negative relative to the outside, results in a resting membrane potential of negative 70 millivolts. Polarization results from two key things. The presence of negatively charged proteins inside the axon. They can't move out. And the sodium-potassium exchange pump that is going to pump 3 sodiums out for every 2 potassiums in. So we get a buildup of more positive on the outside. So it's a 3 to 2 ratio. Sodium exchange pump. Let's take a look at it again. ATP is used to transport sodium ions out and potassium ions in. 3 for every 3, we get 2 pumped in. Excess positive charge accumulates on the outside, and we get this negative 70 millivolts. Because remember, you've got those big negative proteins. Again, take the time and watch this video. It will help a lot. Action potential has 3 stages. The depolarization. Nerve becomes more permeable to a highly concentrated sodium than to potassium. Sodium channels open. So this is when the nerve is firing. We're looking at this part right here, depolarization. So these sodium ions, the small pluses, they're gates. The sodium gate right here, the dark ones, open and sodium moves in. It rushes in. This rapid influx of sodium causes the negative 70 to jump to plus 40. Repolarization. Now we're on the other side of the spike, the action potential spike as we call it. What have you noticed? Well, the sodium gates have closed. And what's now open are the potassium gates. So that means potassium, these larger positive structures, are going to move out. Sodium gates close, potassium gates open. Potassium ions move out, carrying positive charge. Membrane repolarizes, but momentarily it becomes hyperpolarized. It goes from negative 70 down to about negative 90 millivolts. Potassium channels close, sodium potassium restores it. So restores, and some of this potassium is going to leak back out, and we're going to get uh, a negative 70 restored. Hyperpolarization, we just mentioned that part right here again. Membrane potential overshoots to negative 90. Potassium gates close slowly, so more potassium moves out, but it returns quickly to a resting stage of negative 70. So number 2 is depolarization. Repolarization, number 4 is hyperpolarization. Now, we've got to talk a little bit about another couple of concepts here. A neuron must reach a threshold potential of negative 55 millivolts before it will fire. That's the threshold. Once it fires, though, we have what's called an all or none response. The neuron either fires or it doesn't. As soon as it reaches that threshold, the neuron fires. You tap somebody on the knee, tap, tap, tap. You haven't reached the threshold. You tap them just hard enough and the neuron fires. Well, guess what? If you hit them on the knee even harder, it's not going to cause the neuron to fire higher. No. Okay, once it reaches the threshold, it fires. It's like turning lights on. Okay, so your light switch. If you switch the lights on really hard, does it make it brighter in the room? No. You just reach that threshold of tripping the wire, okay, connecting the wires, and the lights turn on. And then it moves like a wave down the axon to the axon terminal. Now, there's a very brief moment, I'll put in this arrow here, where we have what's called a refractory period, the period after an action potential in which this nerve cannot be stimulated. Remember, it's got to go back to a polarized state right here. So this period right here is refractory. Can't stimulate a neuron there. So positively charged ions that rush into the neurons are attracted to adjacent negative ions, and that's going to cause this wave of depolarization occurring. Polarization down the neuron. Now, remember this side here had just fired. This is just fired. So the neuron doesn't, the wave of depolarization occurs this way because all this state over here is still depolarized. Whereas this stage here is in a refractory period. So it can't fire. So the wave of depolarization has got to only move this way. So that's what this is explaining right here. Here's another way of describing it. Now this video, again, watch the video. We want to talk a little bit about saltatory conduction. And this is called also known as frog leaping. And actually, that's how they describe frogs' saltatory locomotion. They leapfrog. That wave of depolarization just doesn't occur like this. In myelinated nerves, the nerve impulse travels very fast because it actually leapfrogs into these nodes of Ranvier that are unmyelinated. Look, that's where the gates can open and close. So when an action potential occurs in a node of Ranvier, sodium ions flow into the axon, sodium ions close, sodium ions diffuses in both directions. Neighboring nodes become depolarized, but left one is in the refractory. So it can, moves both directions, but this is already in the refractory, so it can only move in this direction here. In unmyelinated neurons, there's no leaping and they're much slower. 0.5 meter per second versus 120 meters per second in a myelinated neuron. Now think of babies. Babies are really, really slow and clumsy. That's because their neurons have not myelinated significantly. Okay, so they're more over here. Okay, pinch a baby sometime, and like 2 seconds later, it starts crying. Okay, they're very slow and clumsy. Give it a few years, the myelination comes in, and they've got much faster reflexes. Okay, now a disease that's interesting here is multiple sclerosis. This is where the myelin sheath gets damaged. Okay, so it's like reverse, going back to a baby. Become much slower and clumsy. So this is an autoimmune disease where the myelin sheath degrades, and you can get it myelin degeneration in the brain as well. Okay, okay, I'm going to stop there.